This is the L'Hospital rule for the indeterminate form infinity over infinity. So for this, what it says the theorem is let f and g be differentiable between the open interval from a is a number in the real line, and infinity. Suppose that the limit for f of x when x tends to be infinity is also the same to the limit of g of x whenever x is tending to infinity to be also infinity. So basically it's not determinate. And of course the derivative of g of x is different of 0 for every x in between of this open interval. Okay, if that is the case, whenever the limit of the derivative of f of x over the derivative of g of x exists, I mean is a number inside of the real line in the real set, then the limit of the functions that of course they will tend to be infinity over infinity is also L. So to prove this theorem, we need to recall a few concepts from limits. This is the first one. Whenever we have a function which is defined between a number a and infinity, this is an open interval. It is a function in all the numbers in the real line. Then for L, which is also a number in the real line, L will be the limit of f if x tends to infinity. So basically, if we have this limit, if this limit exists, it means that for every epsilon greater than 0, it could be super small epsilon, but for every epsilon greater than 0, there exists a real number n, of course, greater than a. Why greater than a? Because it has to be between this interval such that every x that is greater than this number implies that this difference is smaller than the epsilon. Of course, always we can do that because the real lines is dense, and it means between any two numbers you will have infinity numbers in between. So there will be a number. If that is the case, it is because f is converging to L whenever x is going to infinity. It means that there is a number that make this f of x very, very, very close than L, such that the difference, the absolute difference, is less than the epsilon. Whatever epsilon you want, there will be a number. We don't know which number, but we know that exists, right? Another thing that we have to recall here is that this is basically the opposite. If we have a function in the interval a and infinity, a function to the real numbers, and the limit that the same limit that we have here, but in this case is the limit is infinity. It's not defined as a single number in the real line, it is infinity. Then for any given alpha in the real numbers, there exists a real number n, of course, I mean between this interval n greater than a, such that for all the x greater than n will imply that the function, I mean the f of x will be greater than alpha. Okay, so I can set to wherever alpha I want, I will find an end that will let x become greater than that alpha when after evaluated in the function. Okay, with these two concepts, let's go to the proof. This is basically how it starts. We have given that, okay, there is an epsilon greater than 0, there exists a number n of 1, because we will have many n's here, greater than a, it means it will be in between the open interval that we were saying here, right? Such that for every x in greater than n of 1 implies that we will have this. This is coming from the first, recall that I call it in this place, but for this one I can say epsilon over 2, right? It's any number. It could be very small, but if it's greater than 0, it means that I can divide it by 2 and still I will find my n1, that these conditions happens, right? So the derivative of the functions f of x over the derivative of a function g of x will be very close to L, such that it will be less, the absolute difference will be less than epsilon over 2, okay? And that is because the limits of these two functions are going to infinity. There exists another number n2, which is of course greater than the first one, such that x, for every x greater than these numbers, f of x will be greater than 0 and g of x will be greater than 0, right? Because these two numbers are going to infinity, these two evaluations, this function will go to infinity. I can make it, I can find a number of x such that the evaluation of both will be greater than 0, okay? So now we have two things. We have this one, and we have that there is a number that will make both functions evaluated in an x that will be greater than 0. Then furthermore, there exists a number n3 greater than n2, such that for every x that is greater than n3 implies that f of x will be greater than the evaluation of f of n2, and g of x will be greater than g n2. Of course, because if the number n2 will be basically less than n3, so we will find that x, right? For any x greater than nt, the Cauchy mean value theorem, remember this Cauchy mean value theorem, implies that there exists a point C in between these two numbers, between the number n2, which is the biggest number that make all these positive, and x, which is a number greater than that even, but below to infinity, such that the derivative evaluated in C is the same of this, right? This part is coming from the Cauchy mean value theorem, so you can see my video where this formula is coming from. And then if we subtract f of x from this function, we will have something like this, right? We will find 1 here because we have 1, and we have to divide it by f of x and g of x in both sides, and we will have something like this. So in here we see that for all the x that are greater than 3, we have okay, we can call this a function f of x in capital, right? If we simplify this from this formula, basically we put it f of x here, and we just put this in the right side, in the left side, we will have something like this, okay? But we know that this function, this part, if we obtain the limit of this function, whenever the x is going to infinity, see, this is going to infinity, this is going to infinity, this function will become 0, right? So we will have 1 over 1, therefore the limit is 1, okay? So now that we have that explain it, to show that this function is very close to L, we write, let's say, the function f of x over g of x minus L in an absolute value. We can replace it by the function that we just obtained from here. So basically this function. And we will have this, okay? But now what we can do, we can add and subtract this term, the derivative of the function evaluated in C from f over g, right? So we add and we subtract, and then we can separate the absolute value. Of course, every time that we do this separation of the absolute value, we have to change the condition here. This is not equality anymore, it is inequality, and this is because the triangle inequality property, okay? So then after we have this, we see that we have in both terms we have the derivative of f evaluated in C over the derivative of g evaluated in C in both sides. So we can put it at front, and we will have f of x this is the f capital minus 1 plus exactly the same term that we have here. So for every x that is greater than n3, in that case, this property will happen, okay? Now that the point C depends of x, but we always have, of course, that the C will be greater than n2, right? We can write this. This is coming from the very beginning of the assumption that we have, right? So now what can we do? Basically, we separated this absolute value, and we let this alone, and this is subtracting here. We move it to the other side to as an addition, right? And we will have basically this part, and then since the limit of this function is 1, we saw that limit before, there exists another n4 greater than n3, such that for every x greater than n4 we have that this difference in absolute value is less than, of course we do the simplification here, is less than this one, right? And this is because x is greater than n4. It implies, of course, that the difference of the f of x and g of x in absolute value is less than the epsilon, the epsilon that we wanted to use to prove the limits. Okay, so therefore the limit, whenever we have f of x over g of x tending to be infinity in both sides, is equal to L, which is the limit of the derivative of both functions. Thanks.